Welcome back. In this video, we start with chapter 3 about 3 important and fundamental theorems in functional analysis: the uniform boundedness principle, the open mapping theorem, and the closed graph theorem. So there will be 3 sections. In this video, I'm going to cover the first section, which is about an important theorem in topology called the Baire category theorem. Okay, here's the statement. If X is a complete metric space and Xn is a sequence of closed subsets of X with empty interiors, then the interior of the union is also empty as well. Okay, this is not trivial because in general, the interior of the union is not necessarily equal to the union of the interiors. Okay. So, in words, we can rephrase this by saying that in a complete metric space, a countable union of closed sets with empty interior has an empty interior. Okay, so before we prove that, let us make some remarks. In practice, we use the theorem in the following form. We have a complete metric space and a sequence of closed sets which cover X. Okay, so X is a countable union of closed sets. Then at least one of them has a non-empty interior. Okay, why this is so? This is just the contraposition, because if all of them have empty interior, then according to the theorem, the union would have an empty interior, but the interior of X is X. Okay, and of course, you suppose that X is not empty. So this is just the contraposition, and we will use this form. Now, if you take complements, we will see that the formulation of the Baire category theorem is equivalent to the following one. In a complete metric space, a countable intersection of open and dense subsets is dense. Okay, prove that. So pause the video, take a paper and a pen, and so this is just a very easy and trivial exercise in set theory. Okay, because saying that the interior of Xm is empty means that the closure of the complement is dense. And when I take complements, closed sets become open sets and vice versa. Okay, so this is very easy. And a countable intersection of open and dense sets is called a residual set. Okay, so we'll prove the theorem in this form, this equivalent form. Okay. So the Baire category theorem can be restated by saying that in a complete metric space, a residual set is dense. Okay. But I'm not saying that the intersection is open, it's just dense, because an intersection of open sets need not be open, as you know. Okay. And third remark, we really need the completeness assumption, because if we remove the completeness assumption, the result may be wrong. So here's an example. If you take the space Q with the usual topology, Q is not complete as a metric space. And every singleton of Q has an empty interior, and Q is a countable union of singletons because Q is countable. Okay, but Q is open in itself. Okay. So we really need the completeness assumption, and you'll see where we used it in the proof. So now I go to the proof. Okay, so as you said in the remark, if you did the exercise that I asked you to do, we take the complements of, so here we have a countable or a sequence of closed sets, okay, whose interior is empty. So when I take complements, the complement of each Xn is open because Xn is closed, and it's dense because the closure of the complement is the complement of the interior. Okay, so when I take O(n) bar, I get the closure of this, which is X without Xn's circle, which is just X without the empty set, which is X. Okay, so I have to show that the intersection of all these sets is dense. Okay, so this is Okay, how do I prove that a set is dense? It's not necessarily open, as we said, but it's dense. A set is dense if every non-empty open set of X meets G. Okay, so we consider an arbitrary open non-empty subset Q of X, and you have to show that Q intersects G at some point X. How do we find this X? We'll find this X as a limit of a Cauchy sequence, and this is where we'll use completeness. So let us construct a Cauchy sequence converging to something, to X. Okay, first step. Since U is not empty, we pick an element X0 in U. And by the openness condition, there is a ball that you can take closed or open, doesn't matter actually. So there is a closed ball of center X0 totally contained in U. So this is the openness condition. Okay, I didn't invent anything. Now, step one. Since O1 is dense, then O1 meets the open ball, or the open ball Bx0 R0 meets O1. Okay, this is the density. At some point, call it X1. Okay. Now, the intersection with O1 and this open ball is an open set that contains X1. So by the openness condition, once again, there is a closed ball of center X1 contained in this open set. Okay? And we may shrink R1 as we wish. Okay, so if so instead of R1, I can think anything smaller would do. Okay? Any number smaller than N1 would do. So I may assume that R1 is less than R0, or if you like, you put here delta, and you take R1 to be the minimum or less than delta and R0 over 2, if you like. Okay, second step, I repeat the same reasoning. O2 is dense, and this is an open, not empty set, so it meets O2 at some point X2. Okay, so X2 is in the intersection of these two open sets, so it's open. So once again, there is a closed ball of center X2 contained in this intersection, and I can take R2 as small as I wish. So I can take R2 smaller than R1 over 2, R1 being obtained in the previous step. Now you guess where all this is heading to. So I repeat the same reasoning, continue in this way. So if you continue in this way, we get two sequences, Xn, in the space X, and it's decreasing sequence, strictly decreasing sequence, tending to 0, Rn, with this property. So at each time, the radius is divided by 2, or is less than the previous radius divided by 2. And the closed ball of center Xn plus 1 and radius Rn plus 1 is contained in the intersection of On plus 1 and the open ball of the previous ball. Okay, so therefore, if we take P to be any non-negative integer, then of course, so Xn plus 1 in particular, Xn plus 1 belongs to this ball in particular. And Xn plus 2 belongs to the ball of center Xn plus 2, which is contained in this ball, so it's contained in this. So actually, starting from, so Xn plus 1, Xn plus 2, and so on, are all in the same ball of center Xn and radius Rn. So this means that the distance between Xn plus P, for any P, and Xn is less than the radius. Okay, so here, this is true for any P. So when n tends to 0, Rn tends to 0, so the distance tends to 0. So we can write this by saying, if you like, the distance between Xn and Xm tend to 0 if n tend to 0. And this is precisely the Cauchy condition. Okay, you can write it in terms of epsilon. So given epsilon, take n large enough so that Rn is less than epsilon, and then we get the distance between Xn plus P and Xn is less than epsilon. And so this means that this sequence that we constructed is a Cauchy sequence. Okay, and now I use the completeness assumption. The completeness assumption tells me that Xn converges to some limit x, and this will be the intersection between U and G. Okay, so as you observed, Xn plus P belongs to the open ball of center Xn and radius Rn. And if I fix n and let P tend to infinity, I know that Xn plus P tends to x. So the limit actually must be in the closure of the ball, which is contained in the closed ball. So the limit must be in this closed set. And this is true for every n was arbitrary. So actually X belongs to the intersection of all these balls. So, or in particular, since by construction this closed ball is contained in On, then X belongs to On for every n, and therefore X is in the intersection. And on the other hand, since we are constructing here a decreasing sequence of balls, so in particular, X is here, so it's in this original, the starting ball, which is contained in U. So X is in U. So X is in the intersection of On, which is G, and in U. Okay. Therefore, the intersection is not empty, and therefore G is dense. Okay. Very simple. So this concludes this small section about the Baire category theorem, and this concludes the video as well. So thank you for your attention, and see you next time.